In physical cosmology, leptogenesis is the generic term for hypothetical physical processes that produced an asymmetry between leptons and antileptons in the very early universe, resulting in the dominance of leptons over antileptons. The analogous mechanism for baryons is called baryogenesis. The lepton and baryon asymmetries affect the much better understood Big Bang nucleosynthesis at later times, during which light atomic nuclei began to form. Successful synthesis of the light elements requires that there be an imbalance in the number of baryons and anti-baryons to 1 part in a billion when the universe is a few minutes old. An asymmetry in the number of leptons and antileptons is not mandatory for Big Bang nucleosynthesis. However, universal charge conservation suggests that any asymmetry in the charged leptons and antileptons should be of the same order of magnitude as the baryon asymmetry. It should be understood, however, that in the currently accepted model for the elementary interactions, the so-called standard model, it is not possible to create only standalone leptons, as these processes are bound by conservation laws such as the conservation of electric charge. Leptogenesis theories employ subdisciplines of physics such as quantum field theory and statistical physics to describe such possible mechanisms. Baryogenesis and leptogenesis are also connected by a phenomenon that happens in the standard model that allows to convert baryon number and lepton number into each other. This makes leptogenesis a possible scenario of baryogenesis, as the lepton asymmetry can partly be converted into a baryon asymmetry. Certain configurations of gauge fields, called sphalerons, can convert leptons into baryons and vice versa. This means that the standard model is in principle able to provide a mechanism to create baryons and leptons, realizing a speculative possibility suggested by Andrei Sakharov in the 1960s. The simplest version of the standard model, however, is quantitatively unable to realize this possibility. A simple modification of the standard model that is instead able to realize the program of Sakharov is the one suggested by M. Fukugita and T. Yanagida. In the standard model is extended by adding right-handed neutrinos, permitting implementation of the seesaw mechanism and providing the neutrinos with mass. At the same time, the extended model is able to spontaneously generate leptons from the decays of right-handed neutrinos. Finally, the sphalerons are able to convert the spontaneously generated lepton asymmetry into the observed baryonic asymmetry. Often, by an extension of terms, the physicists use the word leptogenesis to denote the mechanism here described.